Okay, we're key idea that you're not quite putting your hands on, fingers on, whatever the heck. Key idea, trying to write, talk at the same time, and what I'm writing is not what I'm saying. Okay, so that's confusing to my feeble brain. Okay, key idea. It's the meaning of potential difference. And the meaning of potential difference is the work per unit of charge, right? And work in this case is force times distance. We don't have to worry about a dot product because we've got a thin wire, so motion is in the direction of that wire. The drift velocity is in the direction of the wire, okay? So work is force times distance, right?
Right.
So what does distance have to do with what we're trying to figure out? Well, the work per unit charge is going to be what? The force per unit charge times the distance, which is the length, right? So and I'm replacing distance with length because we're talking about motion between the 2 points, between the 2 terminals of your battery, or along the length of that nichrome wire. Now, what's work per unit of charge?
Electric field.
Huh? No.
No, it's
Oh, wrong one.
Hold on to that answer for a minute. Maybe you can use it in a minute. What's work per unit charge? That's potential difference, right? And it's measured in volts. So I'm going to say potential difference because that's a little better than saying voltage, but you could think voltage, that's fine. You can even say voltage, okay? But we're talking potential difference. This puts you in the context of work per unit charge immediately, okay? Now, what are you going to do about force times length over charge? Well, you could put the length over the charge, or you could put the force over the charge, right? Well, what makes more sense? Talk about the force per unit of charge or the length per unit of charge? No. What makes more sense?
force per unit.
Force
Yeah,
per unit
why?
charge. Electric field.
Because
That's the electric field. I told you to hang on to that answer. So that's, I mean, what possibly, because length per unit of charge have to do with anything, I don't know. Okay, amount of charge per length would be the reciprocal of the amount of charge you got per unit of length, right? Which is related to the cross-sectional area, okay? But potential difference is force per unit of charge times length. I'll just say magnitude of electric field times length. Okay? And from the fact that your potential difference is magnitude of your electric field times length, that's, of course, I guess, be the magnitude of potential difference now, because we're not interested in direction right now. Okay? What can you now determine about what's going on in this circuit? What's the one thing you don't know that you could find? I mean, if you set up a circuit with a battery and a piece of nichrome, what's the one thing you can't measure? Can you measure the length of that wire?
Yeah.
Okay, good, I'm glad you know that. Okay, well,
The
of
field.
course you know that.
It's electric.
Can you measure the potential difference?
Yes. So it's
Yeah,
the
I
field.
mean, if you got a good battery with a low internal resistance, you pretty much know what it is, and if you don't, if you got a bigger internal resistance, you can put a couple of leads across it, right? Of course, then, it gets a little more complicated, but, you know, because when you got current through it, there's also voltage drop, okay? Because of the internal resistance, so, but, yeah, we're ignoring that for the moment. So what's the one thing you can't measure?
The electric field.
But can you determine the electric field? Give you a hint. You've measured the potential difference and you've measured the length of the nichrome.
Yes.
Can you determine the electric field?
Yes.
Yeah. The magnitude of the electric field is the magnitude of the potential difference over the length. I'm not using V because if I use V, you're going to want to think about V equals I times R or whatever, okay? And that gets your brain into the wrong context. That's relevant, we need that to reason this whole thing out, that's what we're trying to get to. But we're not there yet. So, we have this. Now what does this have to do with resistance? Or what does this have to do with the flow of current?
If the length goes up, the electric field decreases, so the force per unit charge decreases, so the charges don't accelerate as quickly. So you have less current.
Perfect. Okay?